Good morning. My name is Phil Stevens. I have the honor of being on the scientific committee this year. I also have the honor of moderating this keynote session with Dr. Micera. As you've probably noticed throughout the course of the week, we've introduced something new this year where we have these 1-minute poster pitches to allow those individuals that scored very highly on their poster abstracts to pitch their work in the form of a 1-minute poster pitch. And so we will have 4 poster pitches at the conclusion of our keynote event. So I would encourage those 4 presenters to come up to the front of the room because we'll be transitioning quite quickly after the keynote presentation. I would also ask those in the audience to keep your seat after the presentation, and as a token of respect to those 4 poster pitches, give them an extra 4 minutes of your time, please, so that they can present their work to you. It is my honor to present Silvestro Micera. Silvestro is currently a professor of bioelectronics at the Scuola Superiore Santa Anna in Pisa, Italy, and the École Polytechnique Fédérale de Lausanne in Switzerland, where he holds the Bartarelli Foundation Chair in Translational Neuroengineering. He received his initial degree in electrical engineering at the University of Pisa in 1996, and a PhD in biomedical engineering from Scuola Superiore Santa Anna in 2000. From 2000 to 2009, he remained at that school as an assistant professor of biorobotics, and in 2007, he won a Fulbright scholarship to study as a visiting scientist at the Massachusetts Institute of Technology in Cambridge. From 2008 to 2011, he led the Neuroprostheses control group as a group leader at the Institute for Automation in Zurich. And the IEEE Engineering and Medicine and Biology Society presented him with the Early Career Achievement Award in 2009 and the Technical Achievement Award in 2021. Dr. Micera's research interests include the development of neuroprostheses based on the use of implantable neurointerfaces with the central and peripheral nervous systems to restore sensory and motor function in persons with disabilities. He's the author of more than 400 peer-reviewed papers and holds several international patents. He's also a member of several editorial boards for peer-reviewed journals in the fields of biomedical and neuroengineering. His topic is implantable and wearable modular neuroprostheses, understanding and restoring neural function. Please join me in welcoming Silvestro Micera.
Thanks a lot. Thanks a lot. Thanks for the very nice introduction, and thanks for inviting me. It's really a great pleasure to be here. I was reminding that my first conference outside Europe was this conference many years ago. So it's really a great pleasure to be back here, telling you more about what we have been doing in my lab for the past 20 years. Before I start the conflict of interest information, I hold shares of 2 startup companies working on the topics I'm going to show to you. So restoring sensory feedback in people with amputation and motor control in people after spinal cord injury. Sensors and action potential neurotechnology. What we do in the lab, it's very different things, starting from something crazy like controlling 3 arms at the same time, so 3 manual control, supernumerary arm control, or we recently created a laboratory in Milan to implant people with paraplegia, with lumbar spinal cord injury, with electrode on for the epidural spinal cord stimulation. So we do many different things. In particular, one of the things that I want you to remember, hopefully, is that we like to play. In particular, my wife is always used to tell me that engineers are still kids, whatever is the age. And in particular, what I'm trying to convince you is that the idea of reusing technology, implantable technology in particular, like Lego bricks, can speed up the clinical translation of different technologies. So please bear in mind the idea of reusing Lego bricks technology for different applications. The very first application, I hope you all know this guy. Somebody does not know this guy? Don't be shy. If you don't know, you have to go out, but don't be shy. So, of course, our dream as a community is to get this kind of performance after hand amputation and the use of a hand prosthesis. And over the past 20, 25 years, I've been working on different things, in particular sensory feedback for the restoration of sensory information. But I want to give you a quick example of what we are also working on for the motor control part. In particular, we are working on the decoding using EMG for single finger movement. And this is something we did with Katie Zhuang, a former postdoc in my lab. And what she did was to show that, as everybody is already working on more and more, you can decode single finger movement using EMG in people with a translateral amputation. But the performance of this decoding, it's quite limited. So if you go outside the lab environment, it becomes very difficult for these people to really exploit this kind of technology. What we are trying to do is to increase as much as possible the complexity of the robotic part. So the idea is to use what we call share control. In particular, my colleague Aude Biard at the PFL developed a remarkable algorithm which is able to move the fingers, of course, in that case of a robotic hand, according to the tactile information that the hand is providing. So our goal, you will see in 1 second, is to use the tactile information for sensory feedback, but why not adding also this possibility of increasing the smartness of the robotic device? This is not for today, of course, but what we did for teleoperation is to see with the robotic hand what could happen if the people are asked to do different tasks. And here you see 4 different subjects. There are the healthy subject that you can see here. And what is interesting to see is that there are 2 of them, which are in general the super users, who do not require the share control. So the share control is the orange bar, while the activity with only the decoder, EMG decoder, is the black one. You see that the other 2 guys really strongly require this share control. So the first message I want to convey to you is that increasing the smartness, even considering the current limitation of the devices, could increase the number of patients, of people who can benefit in an effective and good way by this technology. So share control increase the number of people who can use it. On the other side, most of our activity has been devoted to the control, to the delivery of sensory feedback while controlling the prosthesis. So what I'm doing right now, as you know, is to grasp the remote controller, also using the information provided by the fingers in terms of I'm grasping enough, there is any slippage, the temperature, the position of my fingers, and so on. So our goal is to implant electrode into the peripheral nerve in order to get the information from the sensors in the end and use them for injecting current into the nerves. So the idea is to replicate the neural activation that you get when you grasp something using your natural sensors in your fingertip. And the very first step, and in general, I'm always a bit sad because I have to present 20 years of my life in one slide, but or 15. Let's say we worked a lot on trying to understand the kind of technology which we should be implanted in the nerve. And if you go in the market of electrode for the peripheral nerve, you have different technologies characterized by different level of invasiveness and different level of selectivity. And in general, the more selective, so the richer, the more natural the connection with the nerves, you want to achieve, the higher has to be the invasiveness. So working a lot back and forth with Thomas Stieglitz from Freiburg in Germany and other colleagues, we designed and identified this time electrode, which has a very simple procedure of implant. You enter into the nerve with a tungsten needle, and you leave inside. Here you can see a polyimide, an insulator, a plastic system with the small dots. The dots are the metal contact where they are used for delivering the current. So it's it is invasive because you are entering the nerve, but it's not super complicated for a surgeon to implant it. So with that, we performed more than 10 years ago our first implant. For safety was only 1 month. We work with Dennis, a Danish subject who got the amputation approximately 10 years before the implantation. So here you can see maybe if it works. It does not. Okay, that was the video of the implantation. But the most important thing is when you start stimulating, there is what I call the magic moment. You switch on and you ask the patient, do you feel something? And the beauty of this is that you can cheat the brain easily because the brain is getting the neural activity from the peripheral nerve as in the natural condition. And Dennis was able to refer different sensation at the phantom hand, changing the contact of the time electrode. You see here the different numbers and the different sensations. Not only adding, increasing or decreasing the amplitude of the stimulation in a rude, but you will see reasonably effective way, Dennis was feeling that the pressure was increasing or decreasing. Okay, that was interesting, but of course, this is not the goal. The goal is that you show that the person in a closed loop way can get a benefit, can do something that otherwise will be not possible. And here you can see Dennis was really patient in the Latin meaning of the word because was very kind. We performed more than 700 trials in a week. So was really, really a tough guy and a friend. And in particular, what we asked him was to go up and down, modulating the force, making different level of grasping force, and he did it statistically significantly. There is all the information in the paper. But what I like to show is this red arrow. When Dennis was realizing in real time that he was making a mistake, doing too much force, he was able to modulate the force and readjust it as much as possible. So we can cheat the brain, we can provide the sensation, and this sensation is usable quickly in a real-time way. Not only that, Dennis performed a vast, as I told you, different kind of tests. In particular, he identified the shape of different objects and also the stiffness of different objects. And the interesting thing of this is that if you look at the trajectory of the force generated while grasping, then it's very likely was not using the offset, the final level of the force, but the dynamics of the force, the difference in the dynamics between the two fingers which were sensorized. So if I ask you to do the same task, more or less, you will do in the same way. So it is easy also to exploit in a reasonably quasi-natural way. And then we increase the complexity of what we were doing, because another message, I think you all know that already, is that clearly it's really a loop. So when you realize that with this kind of technology you can do more, then the next step is to go to people like my friend and colleague Calogero Oddo and to say, okay, can you provide me with a technology for the sensorization of the hand a bit more sophisticated? And what Calogero did was to develop a sensorized fingertip with 4 different sensorized mushrooms. This technology can provide very nice performance, and we use it with the first neuromorphic stimulation. So moving from amplitude modulation to something that in general can remember and, let's say, mimic what you get in the normal condition. And with this, we were able to have both Dennis and patient and healthy people with microneurography electrode implanted, understanding different gratings of the texture. So then we are able to have force control, understanding different objects, but also the texture of the object, both in a very simple grading and in the new patients you are going to see in 1 second, also in the absolute value. So it is really possible to get several touch-related information for these patients. Then the beauty of this, I believe, is also that you can enter the cognitive part of the patients. And in particular, with my colleagues Olaf Blanke and Andrea Serino, we developed an experiment where the patient was both getting our electrical stimulation, also embedded in virtual reality. And what we found is that the patient were getting back the telescopic regrowing of the forearm. As you know, in most of the patients, there is no phantom forearm. Playing with this technology, you can play and they can feel back a phantom forearm. Very simple, nothing incredible, but it shows that when we will have, hopefully soon, a technology chronically usable, then the amount of things we can do together will be also on the cognitive side very interesting. Next step, we moved from 1 subject 1 month to 3 subjects for 6 months. Fernando, Almerina, and Loretana were implanted between the end of 2015 and the end of 2017. In a nutshell, we replicated all the results that we got with Dennis, but in addition to this, I want to show you this specific plot. This shows the amount of times that 2 patients, Almerina and Loretana, were referring the position of the sensation on the stump. And in general, you don't want to have them on the residuum, you want to have them on the phantom hand. But in particular, Almerina, she got the implantation 30 years after the amputation. And she were referring more or less all the sensations at the stump, which was not super exciting as a magic moment. But then over time, what happened was that most of the sensation went to the hand. And here you can see her final location of the sensation. So this shows 2 things, that in n equal 1, but even after 30 years, you can use this kind of technology, but maybe in some patients, for different reasons, you need a bit more time to have the game played in the right way and the brain cheated again. So first step was touch, but you know we have 3 different modalities of sensation. The second, which is very important, is position sensation. So the proprioceptive information. And in general, you can, for many reasons we can discuss later if you want, if you stimulate the nerve directly, you cannot elicit this kind of natural sensation. So what we did with Giacomo, Edoardo, and Alberto was to cheat a bit. The idea was to take 1 channel that was giving paresthesia at the wrist, and we made sensory remapping. So we trained the patients, 2 patients, Almerina and Loretana, for 15-20 minutes to understand that the stimulation here was opening and closing of the hand. And a great old friend of mine, the late Sliman Besmaya, that I want to remember here, kind of challenged me and said, I mean, this is remapping, is not going to work. And then we tried to convince him slowly that it was working. So first, the information about the position, we asked the subjects to have 4 different objects, and they were able to understand the size and discriminate well. They were also able to use the natural touch information together with the position information. So even if remapped, the information was still meaningful for them. And then we asked something more, because again, Sliman was teasing me. We ask the patients to have also a dual task. So the patient was doing memory test, counting backward from 100. And even in this case, this is the C, there was a reduction, but interestingly was mainly when the touch sensation was used. Why? Because if I ask you to jump on 1 leg, trying to do some weird movement and then counting back, you are going to fail. So clearly, the more you increase the cognitive load, the more complicated it will be for the patient. But the sensory remapping seems to work, at least for simple tasks. Again, the message here is when there will be a chronic solution, we should not rely only, quote unquote, on the natural sensation we elicit stimulating, but we need to go through learning and training to add more things that the patients, the users can learn. So position. Then we came back, thanks to the help of Sleeman, to the idea of increasing the sophistication of the sensation. When we published the 2014 paper with the amplitude modulation, a colleague of mine made a comment in the press saying that it was surprising that this primitive approach worked. It was not nice, but I got the message that it was necessary to increase the complexity of the stimulation. So we were very lucky at that time because Sleeman developed a wonderful neuroscientific model which was able to generate the firing rate of the different types of natural sensors when you simulate the pressing of the fingertip. So we took that and we used it with one patient, comparing different approaches. The amplitude modulation, the primitive one, the biomimetic one developed by Sleeman, and two different combinations, which are more or less the same thing. And the interesting thing was that only combining the amplitude and the biomimetic solution, you can get the best of everything. For the sake of time, I will not enter into all the details, but if you want to have in this virtual egg test, which is moving, is a box and block with simulating fragile objects, in order to have the best gross manual dexterity, the best accuracy, to feel everything more natural, and to have more embodiment and so on, you need to combine the two approaches, which is really interesting because it, in some ways, not expected. You think that biomimetic works perfectly. But here we are forgetting that the biomimetic solution works perfectly with a perfectly selective interface. If you have an interface which is selective but not perfectly, then probably a bit of burst of the amplitude modulation can help. Other message, there is way more than we should do understanding which kind of encoding you need to have, maybe personalizing also the encoding for the specific user. Next step, thermal sensation. In general, at the end of my meetings and my presentation, there was always, rightly so, a person asking, and temperature? You cannot stimulate the nerve to get thermal sensation because the nerves conveying that information are extremely small. So we are not selective enough to have only that nerve stimulated. But we were very lucky with Soleiman Shokur and Francesco Iberite because 2 years ago, we found that most of the patients, and we can do even more changing something in the patients. We are working on this right now. But the idea is that most of the patients can also have a phantom thermal hand. So by stimulating thermally the residuum, most of the users can feel at least one hot or cold spot on the phantom hand. Not only that, the patients can use this to understand different kind of thermal temperature, different information in real time reasonably well, using a system that this time is only wearable, is not implanted. Is a thermal stimulator that you can put on the residuum and the patients can in real time understand it. So what we did, because of how easy it is to use it, we had one of the patient or the users we tested for the first paper, and then we asked him to come back and we modified his hand prosthesis, changing the socket, adding this hole where we put the thermal stimulator, and we asked the user to perform more tasks. In particular, Fabrizio made many different tests, but the one that I want to tell you more is this bodily contact. If you want, by serendipity, once Fabrizio touched the forearm of Francesco, one of the experimenters, and he said, wow, that's human. So for the first time, getting the feeling that he was touching something warm was giving Fabrizio the feeling that it was a human body, and because of the warmness of the body. So this shows that when we submitted the first paper with the first phantom thermal map, there was one of the reviewers, maybe sitting here in this room, who was saying, why thermal? Why thermal? It doesn't matter. It's not functional. I mean, there is something functional. If you go to Starbucks and it's super hot, you open. But more seriously, it's because this part of thermal sensation is part of our affective sensation. Touching somebody and feeling the warm sensation is also part of our being human and being in contact with others. Next step. I was laughing about myself talking about 15 years of my life with one slide. But I want to thank this guy, Thomas Stieglitz, because he has been working for many years, for more than 10 years, slowly improving the technology of the electrodes in the kind of things that you, in general, you don't publish unless you publish everything at the end. And that was really remarkable because that was the only way to make the electrodes now ready for a chronic implant. And this is what we are going to, if it works, yes, what we are going to do right now. Hopefully at the end of this year, beginning of next year, we are going to submit the files for our first chronic implant. There will be 2 patients with the Hannes hand developed by IIT in Genova, with the printed EMG electrode, a wonderful artificial skin developed by Benjamin T in Singapore. And there will be the 2 approaches that I showed you before. The time electrode for touch and position, and the thermal wearable system for thermal sensation. So hopefully, let's say in 1 year from now, we will have our first patient chronically implanted with this kind of technology. But if you remember, I told you that we like Lego bricks. So what we did with Francesco, Stanisha, and Giacomo is to test the same solution, but this time for leg prosthesis, in this case for people with transfemoral amputation. So the principle is pretty the same. You can see here there is an implant, in this case into the sciatic nerve, and then there is this sensation coming from a sensorized sole. And now both Francesco from the industrial viewpoint and Stanisha from a scientific viewpoint are moving on with this technology. But the beauty of this is that first, thanks to an improvement of the implantation procedure, we were able to achieve a lot of sensation at the foot level. But even more important was the huge clinical impact. So the users were still using their own prosthesis, no change, no super technology used, but they were achieving very nice results in terms of walking faster, with less metabolic consumption, less pain, increased embodiment, whatever, everything. So delivering this sensation, even quote unquote, with the current technology, can have a huge clinical advantage for the users. So that's why we are trying to exploit it. So what I try to show you is that these peripheral and in particular intraneural electrodes can help providing sensory feedback both for hand prosthesis and for leg prosthesis. And that this technology is really ready at least for a chronic testing over time, over years. We'll see how successful, hopefully soon. But then, again, the Lego idea, I want to show you how to use the same technology for a completely different application. So nerve stimulation, but this time not for restoring sensation, but for restoring motor activity. So for people with a hand which is paralyzed because, for example, of a spinal cord injury. In particular, with Marion, Elena, Marco Capogrosso, and many other people, we started working with non-human primates, implanting the electrodes in a very similar way of what I showed you before with users with a transradial amputation. And the very first thing that we found with great, we were very happy to see that in monkeys there was a huge ability in restoring very fine control of the different fingers. So the animal was regaining single finger movement control. Then we said, okay, maybe what we can do is to put everything together. And indeed, with this kind of technology, the animals were able to have different kind of activities, performing spherical grip, cylindrical, pinch, and so on. And also with the remarkable property to have the onset of fatigue starting later with respect with other solutions, so which is also extremely interesting. Then we moved a bit more into the complexity, and with my colleague Stéphanie Lacour, we developed this very small system for creating a short-term paralysis of part of the movement of the animal. So it was only a couple of hours injecting lidocaine, but you see here the animal is trained to grab the handle and to get the reward. In few seconds, you are going to see that when the animal is not able to do that because of the blockage generated by the anesthesia, the animal are pretty smart. So you are going to see that sooner or later, they are able to find a way not to grasp from time to time, but with a less significant performance. And then later you are going to see our first brain control of the peripheral stimulation. So we implanted brain electrodes in the motor cortex of the animal, decoding activity. You see here the cortical activity, and we identified when to stimulate for helping the animal to grasp the different handles. You're going to see in 1 second. So this shows that this time electrode can really perform well potentially also in translational experiments with people with cervical spinal cord injury. And that's why just a few months ago, we performed our first implant in Marco, a wonderful guy who has a C4, C5 spinal cord injury lesion. So the guy is able to use the upper extremity, but very marginally the movement of the fingers. So we implanted the electrodes in the nerves related to the movement of the extension and flexion, so the radial and the medial nerve. What is going to happen next? The next thing is clearly to take all these technologies to clinical practice, at least in terms of first in human and few testing. As I told you, we are going to file in few months the application at the Ministry of Health in Italy for the implants for people, for users with hand prostheses. And we are going to implant the second patient after Marco for spinal cord injury. But more important than this, what I want to emphasize is that now, for the first time, we have all the building blocks. If you want, all the Lego bricks are there. We can decode cortical activity, we can stimulate the cortex, we can stimulate the spinal cord, the peripheral nerve. We have really a lot of possibilities that now we should bring to clinics and to start combining for different applications and for different needs. So hopefully in 10 years from now, at least some of these technologies are going to become clinically available for a large number of people with different problems. And with this, I thank you for your attention. Thanks a lot.
We do have time for a few questions, so if there are any questions from the audience, please come to the microphones in the center of the aisle. I'll get us started while people are making their way up. I'm curious, with the take-home prostheses, how you were transmitting the signals from the sensors in the fingers to the implanted electrodes. Was that wireless? Was that a hardline connection? What connection were you using?
Right now, we are externalizing the electrodes.
Yeah.
But in the chronic test, there will be an IPG, an implantable stimulator, which will be wirelessly connected with the hand. So there will be no wires going through, because otherwise would be... And this took a bit of time and money for the development. So now, hopefully, we are ready to do that.
Very good. Okay, first question, please.
Yeah, hi. Sorry, my name's Jerry. I got 2 questions, if you don't mind.
Sure.
The first one was with the amputees re-stimulating those peripheral nerves, if it had any effect on the phantom pain they experienced.
In general, a huge one. There is a huge reduction until you stop stimulating, then it goes back up. But whenever, and it's not only us, there is many other groups around the world who show that peripheral stimulation means significant reduction of phantom limb pain.
Okay. And second question was, with your thermal feedback system you're developing, if you'd considered using like a carbon nanotube system for direct thermal conduction as opposed to the Peltier system you're using.
Very good point. We are also working on this. Let's say the very first one you saw, it was really the proof of concept, but we are constantly improving the technology to make it, hopefully, we are discussing with the company to make it really a product. You need to work in this kind of direction. Yes.
Thank you.
Thanks a lot.
Silvestro,
Alex.
my name is Alex, you know, Alex Cardetto. I'm a
Yes.
plastic surgeon. Congratulations for the results. They are terrific.
Thanks.
My playgarden is the reconstructive surgery and there the bionic reconstructivity of the peripheral nerve. My question is, when the electrode doesn't work anymore, what the surgeon do then? Remove it or let it there? Because you know, around the foreign bodies there's building a capsula, and it's not so easy to remove electrodes from nerve.
Yes, you know, what we did actually in the patients after 1 month and after 6 months, even if the electrodes were still working, the ethics committee obliged us to remove them. Honestly, I'm not sure it was a good idea, but that's another story. So what the surgeons did was to remove in the 7 patients with no issue. It's not easy, you are totally right, because you get fibrotic tissue.
In a short time it's maybe easy, but if there are maybe patients, they have the electrodes 1 then 6 months, maybe there is a little bit.
You know, on one side, I'm not sure it's going...
At the end is, can the electrodes stay there forever?
Honestly, my answer would be yes. Okay. Because when there is the fibrotic tissue around, the electrode can... What you should do eventually is to remove, if you have an implantable SIM. So other things, yes, but the electrode in the nerve, and that's what I've been trying to fight for with the ethics committee, also for the first patients. I didn't see the reason. There was no damage, no pain, nothing, but they obliged us. But yes, I would definitely prefer so.
Thank you.
Thanks. Thanks, Alex.
Hi, Noelle So from the United States. I'm a PM&R physician. I also have 2 questions.
Sure.
My first question is with the discrimination of the different textures. Did the subjects or patients tell you that, so they were able to differentiate between the different textures, but did it feel normal? You know, so when they were touching wood, they were able to say, hey, this is wood, this is, you know, concrete, right? But did it feel like wood as if they felt it with their non-amputated limb?
Not completely. So clearly the electrical stimulation in general for the naturalness of the sensation, it's limited.
So there was still a learning period to that, or
yes.
Adaptive period. Yes,
yes.
Thank you. The second question I have is about spinal cord injury.
Yes.
So with the stimulation on, with the motor activities, did you find any change in the spasticity or myoclonus in that subject?
Marco has almost 0 spasticity, so is a very mild case, and we didn't see any change. But clearly, one of the things that we need to address in the future, if you want to increase the number of patients, is also to check for this. But right now, you know, you start with the easy, quote-unquote, case.
Thank you.
You're welcome. Thanks a lot.
Hello, Brennan from the United States. Thank you for a wonderful presentation. As you plan to implant electrodes in a more chronic setting, what steps do you plan to take to prevent electrode degradation from occurring?
No, what actually Thomas Stiglitz did in the past 20 years is working a lot, first with the patients, and then in animals to improve constantly the performance. So right now we have animal experiment for up to 2 years, and implant in patient with up to 1 year. And what Thomas did was to change small things in the electrode, which seem to have the electrode reasonably clinically working. Of course, the next step is really to test it.
And in terms of clinical relevance, what would you like the fitness to be in terms of duration before you see it more applicable in a wider setting?
That's a very tough question. I would say my dream would be at least 5 years, at least. But it's my dream.
Sure. Thank you so much.
Hi, Silvestro. Eric Early at University of Colorado, Denver. One of the fascinating aspects of the work that you've been talking about over the past 15 years here is the evolution of sensory feedback and how we think about it from being purely functional to the affective or emotional aspect of that sensory feedback. And kind of building off of Noel's question about the naturalness of a sensation, I think there's been a lot of focus in the field on that. But if you think about something like how your phone vibrates if you're texting, that's not a natural sensation. You could argue it's almost supernatural, but it feels right. Can you talk a little bit about like where the balance lies in the pursuit of natural sensation versus a sensation that feels right in the moment?
Thanks a lot. That's a very important question. In general, the quest for the perfect natural sensation first is impossible because electrical simulation will never do that. And in some way, it's going to move the target in the wrong direction. We need to provide something which is reasonably natural, or at least not disturbing, and then use it. And then show that while using it, it has a functional advantage. Of course, if it is functionally relevant, but then incredibly disturbing, maybe people are, or a part of the people will not use it. So it's really to find, and there was no time, but the combination of the amplitude and the biomimetic frequency was increasing the naturalness reasonably enough. So let's say in a scale from 1 to 10, 10 it's impossible. 7 may be possible, but with this in only few subjects, but we found 5 or 6 instead of 2, which is to me a reasonable number. Because, you know, on the other side, there are colleagues that I do respect. They say, okay, naturalness does not matter. In the long term, if you're using this technology constantly a bit, you should take care of that, but not too much.
Great, thank you very much.
Thanks.
Hi, Silvestro. Rüdiger Rupp from the Spinal Cord Injury Center in Heidelberg, Germany. 2 questions. The first one is, this patient with the spinal cord injury was an I.S.P. So this person had natural sensation, I guess, at least to some level in this event. When you stimulate, do you override this natural sensation? So is he still able actually then to feel something?
It is able. So what you do in general is to find, and honestly, there was a very short-term implant, but the idea was at the beginning to use this information, to have Marco using his own information. So the idea is as much as possible not to overwrite it, but to give the user the possibility to use it in real time.
My second question, also spinal cord injury, you know that in tetraplegic patients then, or patients with tetraplegia, you have a mixture of upper motor neuron lesion and lower motor neuron lesion. And in this case that you showed, it seems that the key muscle of the wrist extensor, actually, then that this was not stimulated during grasping, which makes sense in so stabilizing the wrist joint then for better grasping. So was this denervated, and how do you deal with these problems? No.
What we did actually was to select only the finger electrode. So the idea was to use a passive orthosis for that. Yeah. But in principle, one of the things that we should do, there are 2 that we really need to do in the next patient. If necessary, adding the wrist stimulation, and to get the opponent's policies, which was something we didn't get, which is a bit more tricky. But for us was just one step in entering the field. But let's say definitely the risk movement in a way or another needs to be addressed.
Yes, so thank you very much. And I like your last statement here on the slide.
Oh, thanks a lot. Thanks.
This will be our final question. Go ahead.
Yes, hello. My name is Molly Gustafsson, and I'm from the Jönköping University, a student there. And I was just wondering if the possibilities of nerve stimulation in the peripheral nerve would be possible in congenital amputations as well?
In principle, yes. That's a very important, thanks a lot, very important question. Actually, I've been trying to work on this, but I never found somebody willing to take the risk with me. Because, of course, what is going to change is that you don't have very likely cortical organization which can immediately help with the sensation, probably. So that's the main challenge. But in terms of, let's say, electrical stimulation, yes. What is going to happen? Very likely we will need, again, the help of therapists and clinicians to help us making this functional for the patient. So electrically, yes. Functionally, we don't know yet.
Okay, thank you very much.
Thanks a lot.
I'd like to invite our 4 poster pitch presenters to come stand behind the flag. And as you're coming up, let's thank Dr. Maestro one last time. As a token of the committee's appreciation, we would like to present Silvestro with a Swedish dollar so he can remember this conference as well.
Thanks a lot. Very kind. Thanks a lot. Great pleasure. There is a... Thanks a lot.
Again, each of our poster pitch presenters has 1 minute to do their pitch. I will click after 1 minute. So come on up and welcome.
Okay. Good morning, everyone. I'm Claudia, and today I'm going to talk to you about some engineering innovation needed in pediatric prosthetics. Children grow, their prosthetic socket don't. Recent research has associated poor socket fit with residual limb condition and compensatory movement in this cohort. However, we do not know the long-term consequences on the developing and plastic body of children, but they are likely serious. This calls for significant engineering innovation to address this global challenge. This is why we developed the first ever framework to develop an adjustable pediatric socket, but this can be used for any prosthetics. We have conducted research studies in multiple global locations, interviewing children and prosthetists to identify the unique user needs of this cohort. We have then translated this into technical requirements which have been refined using data from anthropometric analysis, field work, and international testing standard. Thank you.
Hi, I'm Patrick de Mercy, a rehabilitation physician from the University of Groningen Medical Center in the Netherlands. So imagine having an afunctional limb, a flail arm. It gets in the way during your daily activities, and because of the weight, it gives you traction pain. This can severely impact quality of life. So what if an amputation is an option to improve quality of life? That's the goal of the study that we performed. We looked at patients with a brachial plexus injury and an amputation and asked them, what's your quality of life? What's your functioning? Do you have less pain? And well, if you want to know the outcomes, come visit my poster.
Hello, everyone in this room knows the cost and time burden that osteoarthritis is upon an ageing population. This study, the effectiveness of the Unilever, a new product, looked at comparing the new product, an innovative solution, with the market leader. 60 patients were randomly allocated into the Unilever group, the Unloader 1X group, or a control group. The primary outcomes showed that the use of this brace effectively increased the pain-free walking distance in both orthosis groups. You can see this shown on the right-hand side of the screen. Secondary outcome measures also looked at the pain-free walking distance, the pain-free walking time, the functional impairment, looking at the Quince index, and the quality of life of these patients. It's important that a patient gets functional outcomes for a brace, but also it's key that we can get patients to actually wear these braces. So what was critical in the outcomes of this study showed that we had an improved compliance and an improved acceptance of this brace. Future long-term studies will be important to make sure that we get qualitative outcomes long-term with pain relief. Thank you.
Hello, everyone. I'm delighted to be here with you all. My name is Hirokazu Haruna, and I am a physical therapist affiliated with Hokkaido University of Science, Japan. My research focuses on developing insoles that improve forefoot local function in hemiplegic gait. I'll be presenting my research at the poster session. Today, I have the insoles I've developed. So please feel free to try it. Thank you for your attention.
Okay, thank you everyone for your time and attention. Please stop by those posters as they were presented to us. And again, Dr. Maestro, thank you so much.